So this chapter is chapter 17. And in this chapter, we will talk about the acid-base equilibrium. So it's an acid-base equilibrium and solubility equilibrium. So this topic is called the common ion effect. So let's say we have um, a solution of acetic acid. This is our acetic acid, CH3COOH. And the number of moles of acetic acid is 0 0.1 mole. So in the water, what happened? So the acetic acid, so you have to understand acetic acid is a weak acid. It is not one of the 7 strong acids. To find the pH or the concentration of the hydronium ion in this weak acid, we have to do the ice table. Initial concentration, change in the concentration, and equilibrium concentration. So, so I have acetic acid in the water. This is acid. It will behave as an acid and it will donate a proton, H plus, to the water. And it will form hydronium ion, H2O plus, and acetate conjugate base. So an equilibrium will be reached, double-headed arrow. Now we want to find out what will be the concentration of a hydronium ion when we take 1 molar, 0.1 mole of acetic acid in water. Initial concentration of uh, acetic acid is 0.1 molar because we have 0.1 mole and the volume is 1 liter. Do not forget molarity is mole over the liter. So the concentration initial of acetic acid is 0.1 molar. The concentration of hydronium ion and the acetate ion are not present, they're 0. And because they are 0, the reaction will move forward. It will make the products plus plus, and the the acetic acid has to be consumed minus X. It will make plus X and plus X. So at equilibrium, when we add those two components together at equilibrium, the concentration of acetic acid is 0.1 minus X. Equilibrium concentration of the products are X and X. And then we can solve that. If you remember the Ka, we can solve it using the Ka, the value of the acetic acid. You can find it's in the textbook. We can find that the concentration of a hydronium ion equals 1.34 times 10 to the minus 3. And if we will take a negative logarithm of that, we will say that the pH equals 2.87. So we already did that in chapter 16. So now let's say that to that solution of the acetic acid, to this solution of acetic acid, we will be adding 0.05 mole of the sodium acetate. Sodium acetate is a salt, and we have to know from the Chem 11 that the sodium salts of the sodium ion, they are very good, strong electrolytes. They will completely dissociate into ions, a cation, positive ion of the Na plus. The rest, CH3CO minus, will be the anion. So that will perfectly 100% dissociate. So this salt in the water exists as those two ions. So when we take that acid in the water, which has those ions H3O plus and CH3CO minus, if we add to that sodium acetate solution, which has those two ions, really what we are doing, we are changing the concentration of CH3CO minus. You see, this acid already have an ion of CH3COO. When we're adding a salt, we actually have the same common ion over here. This is called the common ion effect. So already the CH3CO minus exists here. When we're adding a salt, it actually has the same ion. And you have to understand, it's like a Le Chatelier principle. At equilibrium, what happens? The equilibrium will be disturbed. Now we have a mole, the concentration of CH3COO minus, so the concentration of that will increase. Equilibrium is disturbed. In order to reach the equilibrium, the reaction or the equilibrium will have to shift, reverse. It has to reverse that, and the equilibrium will be moving toward the reactants. So this is according to the Le Chatelier principle. If we're adding one of the products, we are disturbing equilibrium, and to reestablish equilibrium, the reaction will move away from that to decrease that addition. So now when we add in the salt, because it's already have the same ion, we are increasing the concentration of this ion. The equilibrium will have to move away from that toward the reactant to decrease this addition. So that's what we say. In general, when a compound containing an ion in a common with a dissolved substance is added to the solution at equilibrium, the ionization equilibrium shifts to the left. So that's what we have. And this phenomenon is known as the common ion effect. So the common ion also can be hydronium ion or the hydroxide ion. So one more time, when I will go back here, my acid already had this ion CH3COO minus. When we added a salt, sodium acetate, which has the same ion as the acid, then we have a common ion effect. They're common ion. By adding the salt, we're increasing the concentration of CH3COO minus. We're disturbing this equilibrium. And in order for the equilibrium to be reestablished, the reaction has to shift to the left. So this is a problem. Hopefully you will read and understand this problem. So I will go quickly over it. So we wanted to determine pH at 25 degrees Celsius of a solution that was prepared by adding 0.05 mole of sodium acetate to 1 liter of 0.1 molar acetic acid. So, and another thing is we have to assume that when we're adding the sodium acetate, we do not change the volume. You have to understand, if the volume is changing, then the concentration should also change. So first what we will do, we have to start with the acetic acid. So we'll have to do the ice table for the acetic acid. We'll say initially the concentration of acetic acid is 0.1. Concentration of hydronium ion is 0. But the concentration of this ion is not 0. It is 0 from the acid. But don't forget, we're adding to that, we're adding the salt, 0.05 mole of sodium acetate. It has 0.05 mole of acetate acid. So that's why initially we do have this ion which comes from the salt. Since the product, this one, is missing, that means the reaction has to go forward and make the hydronium ion. So the acid has to be consumed minus X. We have to make this plus X and plus X. And this is our equilibrium concentration. Then we have to put everything in the expression of the Ka. This is the Ka of acetic acid. And then we can say that 0.1 minus X, we can say it's about 0.1, and 0.05 plus X is about 0.05. Then we have to prove if we can do that simplification. And then we can solve for the X. Our X is hydronium ion concentration. And once we find the x, we can put it into that expression, and we can find the pH is 4.444. So the common ion effect, what it did, it shifted the ionization of acetic acid to the left. Less of that now will ionize. You see, less of the acid will ionize. You will have less of the hydronium ion concentration, and the pH will be less acidic, 4.44, not more acidic. So the concept of the buffer solution. So what are the buffer and how can we calculate the pH of a buffer? So buffer solution, or simply a buffer, first of all, it's solution that contains a weak acid. Most acids are weak acid, and its conjugate base. Or it can be a weak base and its conjugate acid. So if we have a weak acid and its conjugate base present at the same time in the solution, or if we have a weak base and its conjugate acid present at the same time in the solution, we have a buffer solution. So what does buffer solution do? A buffer has ability to convert a strong acid to a weak acid. And what it does, it actually minimizes the effect of the addition of the pH. So let's take a look at this example. Well, if we have, let's say, this is if we're adding strong acid, you see, if we're adding to that solution which has a weak acid and its conjugate base, if we're adding a strong acid to that, so what it happens here, the strong acid will find the conjugate base and it will react, and that will not change the pH of a solution. Or if I have, let's say, I am adding a strong base, which has OH minus, to a weak base, and it also minimizes. So the strong base that I am adding here, it will find an acid that will neutralize it, and the pH will not change. So let's go here. So suppose that we have 1 liter of the acetic acid and the sodium acetate solution. So this is our acetic acid. To this acetic acid, we added the sodium acetate. And this is why initially I have the acid present, let's say 1 molar acid. There's no hydroxide here, but I have this conjugate base, or the acetate, which comes from the salt, sodium acetate. The reaction has to move to the right to make for this missing H3O plus. And we can find from here that the concentration of that buffer solution is 4.74. So once again, why this is a buffer solution? It's a buffer solution because it has a weak acid present, and it has a salt of the weak acid, sodium acetate. So when we have in the solution acid and the salt of that acid, so that solution really is, we'll call a buffer solution, because what it can do, it can withstand the addition of strong acid on a strong base, changing its pH. So if I have a buffer solution and I add to that buffer solution a smaller amount of the strong acid, let's say HCl, the pH will not change that much. 4.74, it will not change that much. Or if to that buffer solution, if I will add a strong base, it's also the pH will not change drastically. It's called buffer. So now you have a buffer, and our buffer has pH 4.74. Now let's say what we do, we will add to that buffer solution, we will add 0.1 mole of HCl, very strong acid. We're adding it to the buffer. So now once we're adding H2O plus, 0.1 molar HCl, and 0.1 molar HCl has a 0.1 mole of the H plus or H2O plus. So this is this is our initial concentration of this is the acid. When I'm adding the acid to the buffer solution. That buffer solution has a base, a conjugate base. And that conjugate base, it will neutralize the acid that I am adding. So my conjugate base has the amount of mole 1.0 moles. And the acid that I am adding is a 0.1 mole. When they react, this is accept H plus from here, it will be CH3COOH, and H2O plus becomes H2. All of this H2O plus will be neutralized by this conjugate base. And at the end, you will have no H2O plus left. But conjugate base, you will have 0.9 left because 0.1 mole has to neutralize the 0.1 mole of H2O plus. And you will get the acid. Now you will make a little more acid. It was 1 molar before the addition of HCl. Now it will make a little more of this acid, 1.1 mole. So at the end of that, you see, I don't have no H2O plus left. I do not have H2O plus left. But what I will have, more of this weak acid and a little less of the conjugate base. So now again, I have to put together the ice table with the new molarities here. So the acid is 1.1 molar, H2O plus is 0, and the conjugate base is 0.9. So I will do the change, minus X plus X plus X. This is the equilibrium concentration. I will put this in the expression of Ka. We will find the X, and the X is H2O plus. And we will find that the pH equals to 4.66. Do you see the original buffer solution? Let's go back over here. The original buffer solution has a pH of 4.74. After we are adding HCl to that, the pH didn't change drastically. It changed only by 0.08 pH unit. So that's what the buffer means. So the buffer is a solution that will not change pH that much if the acid, strong acid, or a strong base is added to it. But imagine if we will take the same amount of HCl and we will add it to 1 liter of the water. So do you see the pH of the water is 7. But if I am adding 0.1 mole HCl to 1 liter solution, then the pH will go to 1. Don't forget, HCl is a strong acid. The concentration of HCl equals to the concentration of H plus. It will be 0.1 divided by 1 liter. And I can see the molarity is, what is the molarity equals, and we can calculate the pH equals to 1. So you see that the change is by 6 pH unit. But when I add it to the buffer solution, the pH changes very little. Yes, let's go back to our So this is the how we can calculate pH of a buffer solution. So really what we can do, really, we can use this equation. This equation to calculate the pH of a buffer solution, we can use this equation, which is called Henderson-Hasselbalch equation. pH of a buffer solution equals to the pKa plus logarithm of conjugate base, concentration of a conjugate base, over the concentration of the weak acid. So we know if we had started with the acid has a Ka, then we will find pKa of that, which is minus a logarithm of the Ka. And then we'll take the logarithm of a concentration of a conjugate base over the weak acid. And that's what this problem is telling us. They're telling us that, let's say we have 1 liter of a buffer, and that buffer has 1 molar of acetic acid and 1 molar of sodium acetate, and they want us calculate pH after we addition of 0.1 mole of NaOH. Is a strong base. So when we're adding this base, NaOH is a strong electrolyte that will make Na plus 0.1 mole and 0.1 mole of OH minus. So OH minus in a solution of this buffer solution will should find the acid, and that's the acid that will find this OH minus, and this acid will neutralize this OH minus, and it will make a little more of the conjugate base. Now we will say that I have 1 molar of this acid. It's giving to us the concentration of OH, or the moles of OH minus 0.1, the mole. And now we have the conjugate base, which was 1 molar. Now all this hydroxide will be consumed, neutralized by this acid. The acid will be left 0.9 mole. We will make more of the conjugate base, 1.1. And now you can find what is a pH. You can say, okay, we had the acetic acid, I'm sorry. We have acetic acid. If I convert the Ka of acetic acid minus pKa equals minus logarithm over Ka, I will get 4.74 plus logarithm, a conjugate base. This is a conjugate base. It's a mole, but in a volume of 1 liter, that becomes the molarity. And this is the acid, concentration of the acid. And I will say that the pH equals to 4.83. So you see again, the pH didn't change drastically from 4.77 to 4.83. That's what the really buffer is. Buffers are the solution, but they have a capacity to resist pH change when either acid or a base is added to that. So you see a solution is only a buffer if it has this capacity to resist pH change when either acid or a base is added to it. If the concentration of weak acid and its conjugate base, if they are different from each other by more than a factor of 10, then the solution does not have that buffer capacity. So that acid and its conjugate base, their concentration should not be different more than the factor of 10. So now if I will look at this one, this is the Henderson-Hasselbalch equation. And so to calculate the pH only, so we can use this to calculate its pH only if the following condition is met. If the concentration of a conjugate base over the concentration of the acid is greater or less or equal to 0.1, or it's less or equal to 10. And the log term will vary from -1 to 1. And the pH of a buffer cannot be more than 1 pH unit different from the pKa. Do you see that pKa has a, let's say for the acetic acid, this was 4.74. So the pH will not be different than the pKa by 1 pH unit. So it is known as the range of the buffer. So do you see pH equals pKa plus -1. And if we know that, so then we can actually select appropriate conjugate pairs to prepare a buffer with some specific desired pH. So now if you want to prepare a buffer with some specific pH, you have to look at the pKa. That pKa should be very close to your pH. So this is the weak acid, this is their Kas, and this is their pKa, you see? And if you want to prepare a pH, then you have to look at those pKa, and your pH should be close to the pKa, and then you can use that weak acid and the salt of that weak acid. So they said substitute the pH and the pKa values into this equation, and then you will find the necessary ratio of a conjugate base over the conjugate acid. So let's take a look at this one. They said select a weak acid from and describe how would you prepare a buffer with a pH of 9.5. So you want a solution, a buffer solution, to have a pH of 9.5. So which of those you will choose? You have to choose something which is closer, either HCN, do you see HCN is 931 pKa, or C6H5OH, 989. So you can use one of those. So do you see two of the acids listed? They have a pKa values in that desired range. And so you can put that pH, your pH that you want to, and this is 989, that's the pKa, and you can find that log of the ratio of the conjugate base to the acid should be minus 3.39. This is a log, or 0.41. So one way to achieve this will be to take this of 0.41 mole of this, the base of, the salt of that in 1 mole of the phenol, and then you can achieve the ratio between them, the ratio of the conjugate base to the acid. Okay.